I continue to believe that I have the best job in science. For the last 2.5 years, I've been the editor-at-large for the Journal of Clinical Investigation, and in this capacity, I've acted as chief interviewer for the series Conversations with Giants in Medicine. In that time, we've aired 26 interviews with 28 scintillating scientists. Among them, 2 Knight Bachelors, 8 members of the HHMI, 10 Lasker Award winners, 8 Nobel laureates, 25 members of the Institute of Medicine, and 24 members of the National Academy of Sciences. They've told some amazing stories, some better and stranger than fiction. Their stories are courageous, interesting, compelling, and they've totally captivated me. In this highlight reel that follows, we've selected some of our favorite vignettes from these 26 interviews. This is also here to combine with the JCI's 90th birthday. So happy birthday, JCI.
Happy 90th birthday, JCI.
Happy 90th birthday, JCI.
I've been asked to say happy birthday to the JCI. Well, let me tell you, I do say happy birthday, happy 90th birthday. That's my journal. So thanks for everything you've done.
Happy 90th birthday, JCI. I hope you have another 90, and stop rejecting my papers.
So how did you end up getting recruited to UT Southwestern, and what did you make of the place when you first arrived?
Well, I was very happy at Yale, but you must remember that at that time there were very few medical schools of a high academic type in the United States. Medical schools were just being developed all over the country, but they were new. One of the older and more established schools was Yale, and the section in the Department of Medicine where I was in was very crowded. Almost the entire Department of Medicine consisted of the metabolic division. I was very happy there. They treated me very well, but it was a crowded place. And when I received an offer from Dr. Burnett, Charles Burnett, who had just accepted an appointment as chairman at Southwestern, I decided to take it. I was very naive at the time. I never looked at the institution. I never visited. And when I came to Dallas, it was quite a shock.
I read from your biography that you turned up to the corner that they had indicated and you weren't sure whether or not that was actually what the school was.
Well, when I arrived in Dallas in my car, accompanied by my daughter and my wife, I inquired at a filling station where the medical school was because I wanted to see it. I hadn't visited before. And I drove down where he indicated, and all I saw was a bunch of broken down shacks and garbage. So I thought that I had missed the school, and I returned to the filling station and indicated to the attendant that I went where he instructed me, but all I saw was garbage and shacks. And he said, "That's it. It's the medical school."
Did you regret the choice at that point, or did you consider it a challenge?
Life being what it is, I nodded, and we went to an overnight hotel to face the future.
One of the ironies in my life is that I was raised in a small coal town in Schuylkill County, Ashland, Pennsylvania, hard coal region. And my mother died when I was about 5½. And the irony there is that that brought me to New York. I think otherwise I would have been like all my cousins in that area, remained. It's really quite remarkable that with probably one exception, all my cousins have come back to or stayed in Schuylkill County and the small towns there. So when I came to live with my father's parents in Brooklyn, it was a very crowded household, and I guess not too comfortable. We had my grandparents and my father's older sister and younger brother all living in a sort of 2-bedroom apartment. I think the really very significant event in my life was a teacher I had in high school, Conrad Sapphire, who sort of, I think it's fair to say, adopted me in my junior year at high school. He had lost his only son, who was a Cornell Medical School graduate, in Guadalcanal. And he was sort of determined to try to get me to go to medical school. And of course, this was still in high school. But he was very instrumental in helping me focus on how to even apply to college. I would say that my grandparents weren't exactly interested one way or the other, and my father wasn't around at the time. So he suggested I apply to several schools. The issue, frankly, was that Columbia was the only place in which I could afford to get to, a 5-cent subway ride. And I was admitted to Columbia College, which was a really cultural and life-changing experience. And it was a very exciting time, and we were at war in early '43. And then the so-called Naval Officer Training Program came on the campus, and I applied for and was accepted into that program. And that, by '45, I really completed the requirements for the degree, and the Navy had a program of wanting to send candidates to medical school because they were concerned about having enough physicians in the service. And I took the exam for that and got assigned to PNS. So I was really on a path that was relatively without trauma in applying both to college and medical school. And I entered medical school under the Navy auspices, but by October of '45, the war was over, and we became civilians, and then I got the GI Bill of Rights, which financed most of the rest of my medical education.
Speaking of looking through your CV, I noted one thing that jumped out at me as sounding like it must have been entertaining. In 1980, you were on the USSR Joint Working Group on Space Medicine.
Yes.
So what did that entail?
Well, I mean, I'll be very frank. I think it's perfectly clear I'm perfectly all right now to discuss it. At the time, the Russians had claimed they had solved the problem of weight loss in space, but they wouldn't tell us what it was. They wouldn't tell NASA. So NASA wanted to bring a scientist from the U.S. who was sort of well thought of already by that time as a sort of bait to get the Russians to talk. And that's why I was brought along. I had briefings from the State Department, how I was to comport myself. There were people who wanted me to smuggle things in for the refuseniks. I said, I don't think that's a very good idea, this particular trip, which is under very high scrutiny. And then we were in Russia. We had a wonderful time, but it was a dual opportunity, a dual experience. Our hosts were wonderful and genial, but in the background was the KBG trying to embarrass the delegates. And there were some harrowing experiences. I don't know whether we should get into them or not, but they were quite, the schizophrenic aspect of the Russian society was very evident. They were trying to trap us into doing awkward, stupid things, and involved beautiful women showing up and jumping in our lap and so on. And we were very noble and went straight ahead, didn't get distracted. And there was a wonderful Russian U.S. citizen who was with us. I won't mention his name. I don't even know if he's around anymore. But he said, don't let these people pull this off. Don't let, and the head of the delegation ran away from the table when these people came. He said, don't let them do that. You go and tell them to come back. We'll handle this fine. And then he would insult the Russians in Russian. And they had television monitors in every room. So it was sort of a sick society, but we got through it fine. And we learned the answer. The answer was there was no secret to find. They had poor measurement techniques, so they did measurements before and after the flight, and the error was such that you could make no conclusions. There was no secret. In fact, we have not solved the problem of reversing weight loss in space today. If we went to Mars, we would have people with advanced osteoporosis who would come back. We may be able to use medical therapies. I haven't stayed much with NASA since those days, but it's still a problem. But I wouldn't have exchanged that experience for anything. It was really remarkable. Then we also went to the Bolshoi and had private tours of the Kremlin art treasures. That was done by our host. So it was a very nice experience, but it was certainly bizarre in its range of activity.
First of all, Joe said that I would tell a story, and I will. When I was accepted at the Mass General for an internship, I was the first person in 11 years from Penn that had been accepted, because it was the most competitive.
Correct.
And I was, ecstatic. And then 2 weeks later,
there were only like 12 interns.
There were only 12 interns.
Very competitive.
Well,
that was the top
Harvard.
internship to get.
Right. 6 from Harvard and 6 from the rest of the world.
Right.
So, I was so excited, and then a week later they send you the list of your fellow interns, and there was this guy, Goldstein, from Southwestern Medical College in Dallas, Texas. I never heard. I thought it was a Bible school, and I figured, well, if they're accepting this guy, then maybe nobody applied this year.
Right,
And that's why they accepted me, and so I had very low expectations, and I remember it a little differently. At least I remember admiring Joe's intellect and experience very early. I mean, I put it within the first 2 or 3 days of residency. It was clear that he knew more than anybody else, not only in the internship group, but more than most of the senior residents and half of the faculty. So, but part of it was because of his training at Southwestern. The experience at Parkland, taking care of patients in a county hospital, he had much, much more hands-on experience than I did. So, it was clear that this guy was going someplace, and I just decided to ride along.
I often like to tell the story about this partnership, that there's a remarkable mind meld between the two of you. So, as you know, we find ourselves together at meetings, conferences, scientific advisory board meetings. Sometimes I'm with Joe, sometimes I'm with Mike, sometimes we're all together. But I have found, without exception, if I'm with Joe and I tell him something, I don't care how trivial it is, it could be a scientific fact, it could be a piece of scientific gossip, the next time I see Mike, he knows it. Okay, and this is without exception. And there aren't enough hours in the day for Joe to have related everything I told him to Mike, and vice versa. Yeah. So how does that work?
Let me just say again, it's not just gossip. I come in every morning, and Joe gives me a complete digest of the scientific literature from the night before. Okay, I mean, I have the most privileged existence because I don't have to read anything.
It's amazing. And everything in the New York Times. I have had the experience on many occasions of being with Joe at a meeting, and we come down like at 7 a.m. To catch the bus to wherever we're going. And he says, have you seen this story? Have you seen that? I said, no, where did you read it? He says, in the Times. I said, how did you get the Times this early? But he just kind of smiles.
He tries to get it. But you get off a plane with him, okay? I'm telling stories about Joe, but if you get off a plane with him and you're walking through the concourse, and I'm worried about the taxi or picking up my luggage or whatever, he makes a beeline for the newsstand just in case there's something new out there he can read. And then the internet was invented for him.
Oh,
there's no question that Al Gore invented the internet for Joe Goldstein. It's just
Joe's
two Southerners, obviously.
Joe is the ultimate multitasker. I've had on many occasions the following experience. We'll be sitting at a scientific advisory board meeting for a company, and a very complicated set of slides is being shown. I'm trying my best to focus all my attention on it. Joe's busy on the internet, sitting next to me. He's got his computer out or his iPad, and he's flicking back and forth between 4 stories and this and that. Then he's doing an email. And I say, he's not paying any attention at all. Finally, they get to the end. He puts up his hand. He asks the most incisive question. I said, how is this possible? I mean, how can he operate on so many levels together? Kind of interesting.
So I think all of us, the three of us, are lucky that the internet wasn't invented, that Al Gore didn't come along in our formative years, because we would have never been able to focus. Because I think you've even given a talk on focus.
Right.
That probably is the most single important thing for a young
scientist is to focus. That's
focus and really try to solve one problem at a time.
So in the senior year of medical school, I took an elective with Dr. George Thorne. Worked in his laboratory for a while. And he was a very interesting thing. They were setting up the first American trials with the artificial kidney. The artificial kidney had been created in its current version in Holland during World War II by someone named Dr. Kolff, K-O-L-F-F. Dr. Thorne had heard about this, and he had one constructed in Massachusetts and delivered to the Brigham Hospital. And someone named John Merrill and I were assigned to make the darn thing work. Well, we had to start from scratch. The artificial kidney at that time was a large revolving drum around which something like sausage casing was wrapped, and had a big tank of about 100 liters that you had to dialyze against. Well, there were no dialysis solutions, so we had to start with a yellow pad and figure out, now, how much potassium, how much sodium, how much, we would weigh it out and dump it in, pour water in, and mix it with a stick. That was our dialysis fluid. But the most amusing thing, we didn't have pumps to get the blood back to the patient. So you take blood out of an artery, the pressure of the artery, it would be carried up to a reservoir and then flow by gravity back into a vein. This was acute dialysis. You didn't have a pump, had to make a pump out of an old refrigerator pump. And we didn't have non-wettable substances to suck the blood into and send it back. Now, people don't believe this, but it's true. We hit upon using condoms. And I, as the youngest member of the team, was sent weekly down to Joe Sparrow's drugstore to buy the condoms.
A gross of condoms at a time.
A gross of condoms. And they'd say, here he comes again. I was never held in such high repute as during those few months. Well, we actually did carry out the dialysis. There's a picture in the Boston Globe of standing around the big old dialysis machine with Dr. Thorne and Merrill and myself and his medical student in the spring of 1948. Well, that was an interesting experience.
So your more recent work has been looking into mutations in various proteins that, or genes that cause anything from heart failure to cardiomyopathy. How many has your lab found over the years?
Well, we don't keep a running scorecard. We know that all of the cardiomyopathies, and indeed the majority of congenital heart defects that have a genetic etiology, are profoundly heterogeneous. Mm-hmm. A very poetic fellow in my lab once said, there are many ways that the heart can fail, and he said that after having broken up with his third or fourth girlfriend at the time. So I think that I think that's really true, that there are many, many genes, but what we've been able to do, and perhaps more than the actual number is important, is these genes often function in a shared pathway. And that has provided us the opportunity to cluster genes and the hundreds of mutations in each of those individual genes in terms of insights that are perhaps more illuminary than just numbers of genes and numbers of mutations. Mm-hmm. That's a long-winded way of saying there are you know, scores of genes and hundreds and hundreds and hundreds of individual mutations.
Now, what are you most proud about that you did during your time at the Gates Foundation? What initiatives did you begin?
Really focused a lot on measurement. It's easy to, when you think you're doing something that's for the greater good, that you're actually accomplishing something, but that's not the case. There's so much goodwill out there and so much money being poured into ineffective programs that have no impact. So we really focused a lot on measurement, measuring impact, creating vehicles for this, setting up an Institute for Health Metrics and Evaluation, a health metrics network, collaborating with the International Initiative for Impact Evaluation and so on, and really trying to get a handle on whether we were moving the needle or not. And lastly, I would say partnership. You know, there's an old African adage that if you want to go fast, travel alone. If you want to go far, travel together. And in the world of global health, there are lots of players. There's the WHO, UNICEF, Global Fund, Gavi, and so forth. And how we create a collaborative network to accomplish common goal is something that I think the Gates Foundation tried to do, and that's had a very positive impact.
So let's move on to Avastin and its clinical trials. Initial safety data on a breast cancer trial came back a little disappointing in September of 2002. Were you all holding out hope after the very promising animal model studies, or was it immensely disappointing?
Yes, you're referring to a phase 3 study in breast cancer. Well, actually, it was a patient with advanced breast cancer, relapsed breast cancer. I mean, in retrospect, it was a bit of a long shot, to hope that this drug could. I think the primary endpoint was increasing survival in patients with such a really advanced disease, and it failed, this primary endpoint. But still, in this trial, there was some very intriguing finding, because actually there was an increase in response rate. So even though the trial did not meet that point, it showed there was some biological activity of this drug, At that time, it was very disappointing, but there was really all the success or lack thereof of this program. I kind of was hinging on another phase 3 study in colorectal cancer, previous untreated metastatic colorectal cancer, which was already going on. So we all very anxiously waiting for the result of this trial.
So later, the results from that trial showed a 5-month increase in survival. And the FDA in 2004 approved the use of Avastin for renal cell carcinoma and colorectal carcinoma. So what was your feeling on the day you got the news that it was approved?
It was really stunning. It was an incredible period, because there was lots of negative feelings about the angiogenesis. Everybody would have bet that this colorectal trial would have failed. There was even publication from prominent group that actually predicted that the drug that target VEGF is going to fail, just like another class of drugs called MMP inhibitor. Matrix metalloproteinase inhibitor. So there was actually this sense of inevitable failure of this effort. So it was incredibly refreshing study, see that actually this data could defy these dire predictions and certainly validate a lot of work.
Did you have champagne? Was there a big party? Did you have a parade on the Genentech grounds?
I don't think so. I remember actually I learned the news from actually Arthur Levinson, our CEO. He was so kind, to call me. I was actually in Siena, doing like a week of lecture in this lovely city in Tuscany. I remember I drank a whole bottle of Chianti after I had this news.
I guess the key advance I made was in considering the possibility that what Sutherland had been studying, namely how the endocrine system works, how hormones work on a distant target, such as with glucagon and norepinephrine on the liver and muscle, that might be applicable to nerve cells that a neurotransmitter released from a presynaptic terminal and activating postsynaptic receptors, which were hypothetical at the time, might be analogous. And we found the neurotransmitter-sensitive adenylocyclases in the nervous system showed they were in the plasma membrane. So it became clear that this was a very analogous, that the nervous system responded to neurotransmitters the way the endocrine system responded to hormones, even though there's a millionfold difference in the distances.
And that must have been a rather heretical proposal to have at the time. That
it was. People said unkind things, like this is heretical and nonsense and that sort of thing. The interesting thing about it was that because it was considered so unlikely to be true, I had basically 15 years from about 1968 to 1983 to develop this story. And by the time people accepted it, my research group had laid a lot of the foundation of the molecular basis for neurotransmission. So we didn't have this ultra heavy competition. I've talked to other people who have the fortune of being recognized with the Nobel Prize. And in many instances, it's been the same thing. They've done something very unconventional, and nobody believed them for a while, and then it was shown to be true. And if you think about it, it's more or less the only way the thing could work. If you just did something that was very incremental, it wouldn't be worthy of a Nobel Prize. So it has to be almost invariably something that, occasionally there are different types of discoveries, but many of the discoveries were made where there was a paradigm shift, where somebody did something that people didn't accept because it was not consistent with the prevailing paradigm.
Now, turning to your more recent work on brown fat. Now, you more than almost anyone have a knack for having these studies that get turned by the mainstream media into these headlines. You know, Harvard scientist has a discovery that means we don't need to exercise anymore. We can turn our fat into brown fat. Do you think any of your studies have the potential to get turned into a magic bullet for obesity?
Is there therapeutic potential in these pathways, and particularly in the development of brown and beige fat? Absolutely. I am hard to say certain, but I am almost certain that there is therapeutic potential, and over time that potential will be realized. But I do want to say that the goal is not to develop a pill so that ordinary people need not exercise but can gain some of the benefits of exercise. I think what people have to realize is many people can't exercise. Many people have a genetic predisposition for metabolic disease. You have paraplegia, you have bedridden people, you have the elderly. So, you know, for people who maybe are not capable of exercising enough to provide good metabolic health, it would be fantastic to have a metabolic approach to this, a medical approach to this. I also should say that it is now estimated that up to 15% of the newly diagnosed cancers in the United States are secondary to underlying obesity and metabolic disease. So it isn't just that these people are fat and diabetic. There's a growing epidemic of cancer. It's clear that there's a predisposition for certain neurodegenerative disorders as well. So I think it's a serious medical problem, and it needs a more serious discussion than some of those news articles say, which, I mean, as you can tell, you've hit a sore point. I find them actually slightly annoying, or not so slightly annoying.
How does a proud Southerner, as I've heard one of your colleagues call you, end up in New York City?
I, in medical school, had the good fortune of working with a biochemist in the field of phospholipids.
Camillo Ardom.
Camillo Ardom. And Dr. Ardom had come to this country because of the World War from Italy, where he'd been a pioneer in the field of phospholipid research. I had earlier started out interested in potassium in the heart, and I went to my cardiology professor and asked him, could I work in my free time in his laboratory? And being very honest, he said, well, I don't do anything on potassium in the heart. Why don't you talk to the chair of biochemistry, Dr. Artem? So I went to Dr. Artem with the idea that I'd like to work in his laboratory on potassium in the heart. And he says, John, that's very interesting, but why don't you work on phospholipids? So being in the 1950s, I said, yes, sir. And that got me interested in phospholipids. And the chair of medicine at New York Hospital Cornell was David Barr, who was quite interested in HDL and its link to coronary disease. And I think those interests brought me together with Cornell.
So while you were there, did you continue your research?
Well, not as a resident. I had some conversations with people at the Rockefeller who were working in fatty acids, and but I really only got into research when I got to the NIH.
So how did you end up at the NIH?
Well, NIH was fairly new at that time, and one day at the lunch table where the residents gathered, Richard Silver, who was one of my residents, was telling us about his time at the NIH, and I said, Dick, what's the NIH? And he told me that he had been able to serve in the doctor draft at the NIH instead of joining the military. So I thought that was a good idea, and my chairman, David Barr, managed to arrange for me to get into the NIH program, the Heart Institute program.
Now, as part of your studies of the action of testosterone and dihydrotestosterone, yes, you studied many different animal species.
Yes.
How many different animals did you look at?
I'll have to go back and count them up. I can't answer. It's more than 9, I think. But as I alluded to before, my comparative approach was instilled in me as an undergraduate at UT Austin. But in this case, it was demanded by the following phenomenon. That prostatic hyperplasia, which is a very common disease in aging men and aging dogs, does not occur in any other species. It was claimed originally that it also occurred in the lion, but we were never able to confirm it in looking at aged lions that they in fact had it. So the vast majority of mammalian species do not have prostatic hyperplasia. So it was a logical extension from my standpoint to ask what is different between the prostates that develop prostatic hyperplasia and those that do not. And a student of mine, Robert Gloina, who did the first large comparative study, came up with very clear-cut data, and what he showed was that 5-alpha reductase activity is essential in the prostates of all species in order to get a prostate to form during embryogenesis. But in most species, the enzyme remains active up until the completion of puberty, and then it disappears from the prostate. There's a downregulation of the enzyme in the prostate. But in man and dog, there is no downregulation. They continue making dihydrotestosterone for their entire lives. And so it was that type of study, comparative study, that led us to come up with very substantive data suggesting that unregulated dihydrotestosterone formation was the key cause of prostatic hyperplasia in those 2 species.
You oversaw a legendary doubling of the NIH budget.
Well, that's a bit of hyperbole. I mean, first of all, while I was there and while I was instrumental in getting Congress prepared to do something like that, it would not have happened without a number of other factors. One is that the economy was very strong. Second, we had a Congress that was sufficiently bipartisan to be able to work together on a few issues like medical research. We had strong and outspoken leaders of industry who came to, maybe it's a surprise to some people, to the Republican leaders of the House in particular, including Mr. Gingrich, Mr. Livingston, and other folks who are not always the most loved in the scientific community, and those guys got behind us and made a big difference. Then overseeing the doubling is kind of it's an interesting way to put it, but I was there when it happened. It's actually a lot easier to manage a big increase in the budget than it is to manage what we're going through now, which is flat funding, because you can do a lot of new things without stopping anything. So you have to be a little selective about what to favor, and I did try to do that by making institute directors tell me what they would do with their new money, by indicating special support for the efforts to sequence the human genome, by trying to increase the budgets of institutes that were doing global health, which has become an increasing passion of mine. And yet that all is a lot easier than doing what we're all doing now, which is trying to decide what programs are not performing well, cutting them back or cutting them to zero, and using that money so that new things can be supported.
I think during that year I really fell in love with working in a laboratory. I loved research for lots of reasons. And so through that year I was trying to decide whether to go on to do what was supposed to be gastroenterology training at the Brigham or not. And at the time I was in a bit of a quandary. All my colleagues were out in practice, starting their lives. I was not sure what I wanted to do. And I had a sense, this was 1980, that molecular biology was going to have a big impact on the future of research and science, which I think it has had. And so in order to figure out what to do, I wrote letters to a series of people who were well practiced in the art of the black arts of molecular biology, asking what I should do. Should I do a PhD, do a postdoc, go do my medical training and worry about it later? And probably the most useful letter was from David Baltimore, who didn't know me at the time, and wrote back and said that he thought the Rockefeller PhD program was very well suited to someone with my background, someone who had prior medical training. In fact, years later, I ran into Baltimore when he became president at Rockefeller, and he said, "That letter was from you?" You often showed the letter that I had written him originally, asking what I might do to him. So with that and other inputs that I had received, I decided my best course was not to return to medicine, but rather start the PhD program at Rockefeller, which I did in 1981.
Now, you mentioned two of these aha moments, but there was another patient that changed a little bit about the way that you thought about cardiology, and specifically the surgery with Glenn Morrow, and where you were able to first describe the pressure gradients without an obstruction that went on to later describe that as hypertrophic cardiomyopathy.
Yes, yes, that was an extraordinary experience. So it was a patient whom we had studied at the NIH in 1958. A young man who had a loud heart murmur and symptoms of shortness of breath. And at catheterization, he had a pressure gradient in between the left ventricle and the aortic valve. So he had subaortic stenosis. At that time, the condition that was recognized as a congenital subaortic stenosis was a membrane below the aortic valve leaflets. A pretty rare congenital condition, and that's what we thought he had. It was the early days of cardiopulmonary bypass. It was a big deal. At that time, I had returned from Hopkins, and I had an intermediate position before I became chief of cardiology. I was the head of the cath lab. One day, I'm doing a cardiac catheterization when a message comes from the operating room Dr. Morrow wants to see you up there immediately. It was quite enough awkward because I was doing catheterization, I had the patient on the table. So I got somebody to take over for me because it was an unusual request. I got to the OR, open heart surgery at that time, you know, there was a cast of thousands. Many people in the OR, a gaggle of anesthesiologists. It was, you know, it was the very early days of the program. Pump technicians, hematologists, obviously surgeons and their surgical assistants, scrub nurses, etc. And I come into the operating room, and Morrow is bent over the patient, and he said, you know, Gene, you have screwed up. He said, he doesn't have subaortic stenosis. I said, what do you mean? He said, well, he said, I arrested his heart, which is a big deal. It was a big deal at that time. He opened the aorta, and he put his index finger through the aortic leaflets down into the body of the left ventricle. With his left hand, he put his finger through the left atrial appendage into the left atrium, into the left ventricle, so his fingers met in the left ventricle. He says, there is no obstruction. I've got free flow here. And I said, I don't know what is going on here. He said, well, you've made some terrible error. Well, I was horrified and concerned. I said, I didn't know what could have happened. He was upset. He was a pretty cool customer, but you know, something obviously had gone wrong. And I finally said, well, I don't know what to say, and I have a patient on the table, so I need to be excused. And as I walked out of the OR, I said, but Glenn, if you get his heart started again, and I said if, not when, because if you opened the heart and had somebody on bypass and arrested the heart, unless you fixed something, you made the patient worse. Please stick a needle into the left ventricle so we can measure, so you can measure the pressure in there. And I was devastated when I walked out. He came back, he came down a couple of hours later, came in and was obviously mollified. He said, the boy's going to be okay. I said, that's great, thank God. He said, and you know, I measured the pressure, there was a big gradient. I said, well, how can that be? He said, I don't know, how can it be? So what was going on? And he said, well, I don't know, you know, that heart seemed normal. It was a little hypertrophied, and so we puzzled about that day in and day out. About 3 weeks into this, he finally said to me, he said, you know, he said, I've been in this longer than you have. I'm older than you are. No, he was 36 and I was 29. He said, I can tell you, in medicine, sometimes you come across something that you just can't explain. And you don't want to get stuck there. Sometimes you just get paralyzed, and we just gotta move on. I said, I guess you're right. And that's the way it was for another month when a second patient presented with exactly the same thing. By now, we were alert to this. And we also became aware around that time that a patient had been studied in London like this. So, of course, we followed these patients, made sure they were okay, and published a paper about them. And we didn't quite know what it was, but we did feel it was an obstruction that was caused by hypertrophy of the muscle. And that led to an intense interest in this condition. We got a lot of patients. They certainly came up because open heart surgery began, and they were misdiagnosed because they had a loud systolic murmur. So before the condition was recognized, they were thought to have either a ventricular septal defect, which produces a loud systolic murmur along the left sternal border, or that they had mitral regurgitation, which produces a loud systolic murmur, but that's a little further to the left. And so we accumulated a large series.
Now, in preparation for this interview, I read a fair bit of the previous interviews that you have given and some of your biographies. And in one of the interviews you'd given in the past, you told the interviewer that there was a moment when you were facing so much uncertainty about the nature of your research that it was hard to get funding. So you were finishing your clinical training with 3 small children. You had to take a trip and you had to spend the night either in a movie theater or on a park bench. And on one occasion you had to smuggle a lab rabbit out of your lab at Northwestern in order to...
Oh, those were true stories.
So how did you weather that period of uncertainty and keep persevering in what must have been just an undaunting and difficult task to accomplish?
I don't know that I gave it the kind of deep thought that that you're implying I should have had, but somehow I thought that everything was going to turn out all right. But I think that the greatest source of anxiety was not so practical as all that. I didn't know for sure what to do, and so I described in one of these little things that were prepared for the Lasker Prize that that I referred to myself at one time as a missile searching for a trajectory. I was bursting with energy. I really wanted to do something that wasn't conventional, wasn't going to be bread and butter surgery as a means of making money, but I wanted to do something important that would have a life of its own, that would endure. But what to do? I had come to be regarded as a dilettante, having gone through a PhD in neuroscience and then a PhD equivalent in working out the heart block problem, and here I was wandering around, not pursuing either field. I just didn't know what to do with myself, and I was also getting pressure from my father, who was getting sick of sending me money, and I was getting pressure from my first wife's family, who had means, but they didn't like the idea of providing a dole, and I was even more uncomfortable in accepting it, that kind of help. So the problem was really what field I should be working in. And at that time, at the height of those concerns, when I went to Philadelphia, it was to be certified or to go through the examining process that would make me a qualified thoracic surgeon. And now I had, and I had all those skills in cardiovascular surgery and in just about in every field in general surgery that had been acquired over an educational period that had lasted from the time that I got out of the Navy, now for like 13 years, perpetual student syndrome, or a dilettante syndrome. Well, I like to think of myself as a gifted dilettante, but being a dilettante in and of itself is not a good idea.
Usually in these interviews, I ask the MD subjects that I have if there was ever a patient that impressed them or that helped them learn something. But from reading your book, Medicine, Science, and Merck, there was an anecdote in here that I'd actually like you to tell the audience about. Well, since you were there during the doctor draft and you were part of the public health service, you were actually considered to be brought up to be court-martialed for insubordination. And this was over patient care. Can you tell me the story a little bit more?
Yeah, well, yes, that was an interesting experience, which I tried to forget. The incident was my coming in after a weekend in the National Heart Institute, where my job was to take over the patients who had been admitted to the National Heart Institute over the weekend. This was Monday morning, and I walked in. And you have to remember that I'm a proud graduate of the Mass General Hospital, thinking, you know, pretty well trained at that point. And I was handed a patient where I was told that the patient came in, a man who was having a major problem with seizures. Seizures, pain in the chest. It was admitted with the idea that some problem with his heart, or potentially his nervous system, his brain, because he was having these major seizures and chest pain. And so I examined the patient and could not figure out what he had. But because I didn't find anything wrong with his heart, and I didn't see anything in his lab work that would suggest what the diagnosis was. And so I wrote a note immediately after seeing the patient that as far as I could tell, the heart was okay, and everything I saw in his study of his head was also normal. But I was insecure, and so I asked for a consultation by one of the top neurologists in the National Institute of whatever it was. Yes, right, neurological diseases and blindness. And so sure enough, the top clinical guy in the Institute came to visit with an entourage of people and examined the patient, looked at the x-ray of his skull, and pointed out that there was a problem there. And I looked, and I did not see what he was pointing to. And so he then looked at the chart and looked at my note and said, you know, whoever wrote this note, it's not very good. He made some derogatory remarks, which really floored me, because I hadn't been used to that kind of treatment at the Mass General Hospital. So when he left, you know, he felt that this man had a neurological problem as seen in the skull films. When he left, I wrote a note. I typed a note to him saying that I thought he was inappropriate in the way he had reacted to my examination of the patient and my opinion. And I said some other things I should not have said, which were very unfortunate. But I was pretty much angered by this interaction, and so I determined to figure out what this patient had. And I was sure he didn't have heart disease, because I was pretty good at that. I couldn't be sure about the other, but the significant thing, he was having grand mal seizures, what looked like grand mal seizures. He would bite his tongue in the evening and pee in the bed, and ask, and said he had pain. And the nurses would come to him, and he said he needed morphine, because that's what he was used to. They would deliver the morphine. So I set up to watch this. I set up in the doctor's quarters, but right opposite, I was sitting actually in the nurses' area, in a place where I could watch through a crack. The door was left open just a little bit so I could watch him during the night. And I noted that he would, well into the evening, start having his so-called seizures, writhing in the bed and peeing in the bed and biting his tongue, and ask for morphine. And so as I saw that for a couple of days, a couple of evenings, And then I made some calls to the city hospitals to see if anybody else had seen this guy. And sure enough, he was a known figure in the city hospital system. And they said, "Oh, you've got Charlie up there." And I said, "Charlie?" "Yeah." And they said, "Oh yeah, he does this kind of thing." And so I confronted him and said, "Look, I know you're faking this stuff." I offered him some money to take a cab, and he got out of bed, and he took a cab and went away. This neurologist had gone to the head of the National Heart Institute asking that I be court-martialed, and instead I had a presentation to the clinical staff of Munchausen's syndrome, which is these patients who pretend that they have some kind of medical, in order to get something out of it. It's usually drugs. At that era, it was drugs. And so he disappeared, and I learned definitely not to write notes of that sort. But it was an experience that I was happy to get by. I was not court-martialed, in fact. I stayed at the National Institutes of Health. Instead of 2 years, I stayed for a long time.
Now, can you describe how it felt to actually land on TLR4?
Oh yes, I can tell you exactly. It was something that happened rather late at night, maybe around 9:30 or so at night. I was back at home in my study, and I was looking over the day's blast results, and we had been through a long dry spell where we had just seen nothing in the other backs approaching the margin, and I was getting very anxious because I knew that either we had to find the mutation soon or we had mapped incorrectly and we were just in the wrong region of the genome. And that was almost unthinkable, but I do remember discussing with Alexander Poltorak, who was the lead postdoc working with me on that project, the possibility that we would have to just go past our limiting markers and keep looking up and down the chromosome until we found it. And that was a really daunting prospect. Anyway, suddenly there was a very strong hit with the blast search, and nearly perfect identity, over 600 or so nucleotides. And that was a stronger match than I'd seen anywhere in the CONTIG before. And within a few minutes, there was another hit with the same gene. We were in a back called I-17, and we had just begun to explore it. And these two hits were both at different ends of the gene, which was very lucky for technical reasons, because it enabled us to know the sequence and make primers and amplify the whole thing. But I was very excited. I was hyperventilating. I was kind of shaking. I made a phone call immediately to Alexander, and I could hardly tell him what I had seen because I was so excited about it. And the reason to be excited was partly the nature of this gene, that it had leucine-rich repeats, and therefore was similar to CD14, which was another protein known to be required for LPS sensing, though not the transmembrane receptor. And I thought that made a good story. And also it had a cytoplasmic domain similar to IL-1 receptor, which wound up also in the same list of hits in the blast search with one of the fragments that we had analyzed. And of course that is an inflammatory receptor that's known to activate NF-kappa B. And I had a vague memory, which I confirmed in a few minutes, that someone in France had earlier looked at toll and found that it was needed for flies to resist fungal infection. And here I knew that TLR4, if this was indeed the gene, would be required to resist gram-negative bacterial infection, so it made a beautiful parallel evolutionary story. So all these things were very exciting, but we had certainly to find the mutation, and we had made up nice stories about all the other genes or pseudogenes that were in our CONTIG before.
So we were able to develop these methods, and then Fionnuala Brennan was able to do what was the pivotal experiment, which is to put in antibodies to TNF into a mixed synovial culture and show that interleukin-1 and then lots of other inflammatory cytokines were downregulated.
So this quickly took off, such that in 1992, you and Tiny Maney started your first open-label, non-blinded trial in 20 RA patients that were otherwise refractory to other treatments at the time. Can you tell me a little bit about how that went and your excitement at the time as the data was coming back?
Well, the excitement was very palpable, but there were a few little hurdles, one of which was that we had developed this idea based on the blockade, the TNF blockade downregulated other cytokines, that it was the therapeutic target. But everybody and his brother knew that autoimmune diseases were driven by CD4 T cells, and so the companies that were starting to work with monoclonals were very busily trying to cure rheumatoid arthritis with anti-CD4 antibodies. So as we started to try and get some traction on our idea, we quickly found that they weren't interested.
You've spoken in the past about how you did your science because you were driven by scientific curiosity, not by winning prizes or getting honors. But surely sharing in the Nobel Prize with Ernie Rose and Avram Hershko in 2004 in chemistry must have been very sweet. Can you tell us a little bit about that time?
You know, obviously we are happy about it. I think that all three of us, and we did not appeal the decision. But I got it relatively young, and you celebrate for one day, and then you celebrate the second day, and the third day you have to decide what you are going to do with yourself. You cannot celebrate forever. And I decided to do two things. First of all, to continue my science, and we do continue science. Actually, we are doing now, I wouldn't say better or more original science, we are doing I think that we are doing good science now. New paradigms in the ubiquitin field, monoubiquitination as a signal for degradation, collaborations with synthetic organic chemists. We are now being able to conjugate, to synthesize ubiquitin conjugates that we never able before. Milligrams amount of a defined conjugate, a protein, with ubiquitin sitting wherever you want to put it, or even a chain of ubiquitin. It's an extremely powerful tool to understand the proteasome and so on and so forth. So we are doing, I hope, good science. So this was my major decision, because otherwise I will feel that, you know, I was cut off my umbilical cord and I became kind of a spaceship. But then I decided also to leverage my new position to two major issues, handling, if I can. One is education of kids in Israel and worldwide, mostly by showing them that it's possible, that it's not in heaven, that it's not a Nobel Prize, it's the achievement behind the Nobel Prize, it's their hands reach. There are a zillion of scientists who are better than I am. I mean, they discovered things. It's not the Nobel Prize, it's that you can make a difference, you can make an important discovery, and human beings are doing it with genes, with, you know, that talk to you the same language, that are excited, that can curse in your language, that are familiar with your culture, that talk your language, especially in Israel, that I can talk the language and curse and know the history, and I can share with them values. So this is one thing, and I think that it really excites them. It really excites them. You talk to them at their eye height, which is very important. They come and grab you and take photos with you, and you sign them, and you joke with them, and they see, wow, it is possible. And many people, many kids are writing to me back. You made it to me. You know, you made my day, you made my decision, you helped me, you assisted me, you excited me, you are illuminated my road. So, and it's important. And I do it on a personal level. I don't write big educational program. I try to talk to politicians, but this is useless. I know that talking to politicians is important because then you can magnify your voice. But I don't know. You know, everybody does what he likes to do. But talking to the kids, it's fantastic. So doing my science, education, and getting familiar with the Jewish, you know, the opening of the gates of the world. That's here I'm abusing my celebrity quote-unquote position, because I'm invited, I insist wherever I go, especially, and I built very close relations with remote Jewish community. Greece, which is only an hour and a half flight from Israel. You know, I have terrific relationship with the Jewish community there. I speak in sermons in their synagogue. I'm visiting them. You know, there were 500,000 Jews in Greece. The Salonika was a Jewish city. You know, all the harbor was operated by Jews. They were all perished. 3,000 Jews were left out of 500,000 in Greece. How they can lead Jewish life? How can they marry? How can they have kosher food? How can they do anything? It's really fascinating for me. And I think that I feel when I come and talk to them that I blow unbelievable wind in their sails. They inflated. I inflate their sails. And it's really a very good, I feel belonging. I'm not, you know, many scientists are doing science. I feel deeply rooted in my parents' heritage, in what I am, in where I come from. It's important to me.
And it was an awakening.
It was my only epiphany of my life. But so Silverman gets up, this little guy gets up, he gives this talk, he tells this story that the bacteria don't glow like this, then they do glow when they're in a group, and then he knew about the molecule. And anyway, so he gives this little talk, and I'm just sitting there, and I had never heard anything like that in my life. We all, meaning everybody and the microbiologists, all thought that bacteria were these asocial recluses. They just divided in half and each cell did its own thing. And here's this guy saying, no, you know, the way they do it is by doing this bioluminescence together. And I just remember thinking, that is either the coolest thing, you know, I've ever heard, or this guy's a nutcase. So Silverman gives this talk, and I just thought, that's amazing. The bacteria are acting as a group. And remember, this fits into Bonnie's idea of how do bacteria sense the world, right? I'm working on a similar, a different behavior. And then I also thought at that moment, and then the rest of his talk was all about the genetics, finding the genes, you know, and I didn't understand any of that. But I did get that the way he did the screens was you made mutants, whatever that meant back then. You turned the lights off and you look for bacteria that were glowing when they shouldn't be or not glowing when they should. And I thought, I am smart enough to turn the lights on and off in the room, right? And figure out which ones are dark, right? So I literally, when his talk ended, I like ran up to the podium and I said, you know, you just have to let me be your postdoc or I'll kill myself. You know, I mean, something like, not the best, you know, interview strategies, but I literally like just, you know, and said, you just have to let me come work for you. And so eventually he did. He's a very shy person and I'm not, right? And so I think he probably worried that this might not have been the best match, right? And then the other thing is that he took each of us, in his career, he took each of us one at a time, right? And so we would come, so he only had, I don't know, 5 or 8 postdocs in his whole career, right? And he would take each one of us and we would work on something big, he and you, right? And then you took it all and he would start on something else, right? That is the way science is not done anymore, right? Like, we all have more, it's a bigger machine now. We all have more people so that when a postdoc takes something, I still have something, but he just, I mean, I remember so then I got to his lab and I remember the first day, you know, he just said, what you get is what you take. And I'm like, where are the pipettes, right? And so he was the most amazing mentor because he was so generous. And also, right, most of the time I was the only one in the lab. You know, so it was he, and there was a technician, Miriam, right, who'd been with him for 20 years. And so the 3 of us literally worked together for 4 years. And it was just this utopian postdoc, because I got there. Remember, I don't know what a gene is. I don't know what a restriction enzyme is. He's like, let's do a transposon mutagenesis. And I'm like, transposon? You know, like lambda. I never heard of any of that, right?
Synaptobrevin, synaptotagmin, RIM, MUNC18, more recently, Neurexin and Neuroligin. You've spent your career showing us exactly what the mechanism of neurotransmission is and the proteins that are in there. how have you managed to have this singular focus? And can you tell us about what it was like during that phase of your career, of these discoveries?
I think it is often confusing for people who are not in this field to have, you know, it's almost like a zoo of molecules that are all sort of mixing and matching. They all have these strange names, just like animals, I suppose. Yeah. So my focus on synapses is driven by my continued belief that understanding synaptic transmission is absolutely crucial for understanding any brain function. And high level, low level, memory, immediate reactions, anything, vision, perception, thought, consciousness. And I think we need to understand this at a level that cannot dispense with the insights into molecular mechanisms, because I would argue that molecular mechanisms underlie, for example, memory. Having said this, which is not exactly the question you asked, it does get there. So, there clearly is, I mean, the synapse is obviously going to be complicated. It's not going to be any less complicated than a ribosome, than protein translation. And anything that, when you look close, becomes complicated, because if you're a physicist and you study atoms, it becomes complicated, right? So, how can we actually deal with the complexity and the many components? And one way to do this is to try to identify what components are there. Then subsequently try to figure out which ones of these many components are the ones that actually matter, and which ones are the ones that are not going to provide major insights, which ones are the ones that are going to have really consequences for our understanding, and then focus on these components. Among the list of proteins you mentioned, all of these turned out to be proteins that are of absolutely central importance. But there's many, many others I have studied over the years that you didn't mention. That I spent many, many, many years and a lot of papers on. And that to this date don't really have a well-known function, and probably are important in some way, but are not central players.
So I wanted to study the interface between the immune system and infectious diseases. And that's really important, because that is something that I wanted to do 10 years before HIV came along. And as the history unfolded, when HIV came along, that's one of the reasons why I made that dramatic shift, much to the dismay of my mentors, who I had a very successful career. The trajectory was like that, and the things I was doing with inflammatory and autoimmune diseases. And then in 1981, when the first reports of gay men from first Los Angeles and then New York, San Francisco, and Los Angeles came in, I remember reading it and saying, oh my God, this is a new disease. This is really what I want to study. It's clearly an infection. We don't know what it is. It's destroying the immune system. So who better than someone who's an immunology infectious disease person to study this? And that's when I essentially stopped what I had been doing so successfully and started bringing in HIV-infected individuals who we didn't know it was HIV at the time. I remember my mentors looking at me saying, why are you doing this? You're throwing away a potentially great career. And I said, no, 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 this is going to really be big, trust me.
So let's talk a little bit more about that time, because I can imagine as a clinician, it must have been a very heady, frustrating, depressing time.
Yeah.
But yet, as a scientist, as your lab was starting to really figure out the early steps of HIV pathogenesis, and then later on, the early aggressive viral control, that must have been quite invigorating as a scientist. So it's just a mix of emotions. I mean, what were you going through at that time?
It's exactly that. It was a complex of emotional highs and lows. If you look historically, I came back from my chief residency in 1972. And from 1972 to 1981 were the heady years of developing essentially curative therapy for Wegener's granulomatosis and polyarteritis nodosa and the systemic vasculitis. So I, for 9 years, was someone came in with a disease that historically they were expected to die, and I would give them the Fauci protocol, and they would get better. And they would get up out of the hospital, walk out, their family loved me, they loved me, and all of my patients were doing well. So it was an extraordinary period. Then when I went into HIV, I describe it as the dark years of my professional career and even the dark years of my life, because every one of my patients died. I mean, and I brought in hundreds of patients during those early years. The median survival was 6 to 8 months at the time when we didn't even know what the virus was, and we certainly didn't have any therapies. That means that 50% of my patients were dead in 8 months. That was a terrible feeling on a day-by-day basis. But as you point out correctly, every time you made another observation, it was a new observation. I mean, we started off making observations about pathogenesis before we even knew what the virus was. The paradox, one of my first papers in HIV was in the New England Journal of Medicine, in which I described the aberrant immune activation, the paradox of an immunodeficiency disease in which the immune system was aberrantly turned on. I had no idea what that meant. I kept on scratching my head. Isn't this interesting? Hyperaberrant immune activation, and yet immunodeficiency. What is going on? And as it turns out, you fast forward 10, 12, 13 years when we really got our arms around things, when we had the virus and were able to study the virus and we could treat people and bring the virus from 500,000 copies down to 40 copies, that immune activation is actually the driving force of HIV replication. Mm-hmm. So it's a paradox that the virus turns on the immune system, activates it, and the very activation is the thing that drives virus replication. And we didn't know that when we made that first observation in 1984. We had no idea.
One of the main messages that I've seen you give in the media at large is that there's a genetic underpinning to obesity. Do you feel, or have you noticed that over the course of your career, there's been a shift in attitude towards obesity? I mean, why is it that obese individuals are portrayed in the media as being so repugnant?
It's fascinating, and I don't think I'd hoped we may have changed and shifted things, but I don't think we have, frankly. I think that the vast bulk of public literature on obesity is condemnatory and is accusatory, and, as you say, portray the obese as almost uniquely unclean. I mean, there's almost no human condition which carries with it so little sense of sympathy or sense. It's fascinating, and that has been very difficult to argue against. Even though we've known for 50 years that the heritability is extremely high. I mean, it's really apart from height, it's one of the most heritable phenotypes that we have, and of course it's because everyone has a deep sense of that they understand the nature of their own body weight and why they're lean and why others, and naturally lean people like to think, well, I'm lean because I'm in control and I know how to control myself. So those other people, how could they let themselves get like that? They must have such lack of control, and this is therefore a moral choice that they've made, and it's very easy for it to be confused with moral choice. But it's still. I would like to do a sabbatical, I think, sometime in a philosophy department to try and deal with the nature of the repugnance with which obesity is viewed compared to, I mean, I view it much more repugnant to cheat on your taxes or to cheat on your spouse, for example, or to park, if you're not disabled, parking in disabled spaces. So why are all those things in a way much more acceptable than being fat? Because being fat simply doesn't bother anybody. It doesn't. It's just you're there and you're fat. And, why should it cause such a tremendous abreaction? And that's not something molecular biology is going to tell us about. So I think I may need to do a sabbatical in an Institute of Advanced Studies somewhere.
At the height of the AIDS-HIV pandemic, you were living in San Francisco, doing excellent work on HBV, but you decided to switch to KSHV.
Yeah.
Why?
I remember being about 40 or so at the time. And I remember on that particular meeting, all of the plenary session speakers were people who had been very influential when I was in school, in medical school and undergraduate, and many of them got up and gave talks that were still about the very same problem that they had been working on when I was a kid, and I remember, and what was striking was it was one after another of these people by this time they were all in their mid to late 50s, very accomplished, but they were all still working on the same protein that they'd been working on, asking variants, more refined variants of the same question. And I remember just being struck by that, especially compared to the example that Harold had set, where he'd started out working on RSV, and then it started lateralizing to a whole series of other retroviruses, different aspects of the retroviral life cycle, initially reverse transcription, later integration and oncogenesis, and then off into hepatitis B, and later, he was even at the time experimenting with telomeres with Tizia delonga. And I saw, on the one hand, this example of somebody with a restless intellect and taking on new challenges. And then I saw the opposite profile on the podium at ASV. And I remember walking out of that amphitheater at the end of that meeting. And I couldn't figure it out, but something was wrong. And I was like upset. And when I got on the plane, I realized what it was, is that I did not want, at the age of 50, to be working on the self-same thing I was working on when I was 37. By this time, the AIDS epidemic was well underway in San Francisco, and during my attending months on the ID service, we were seeing an awful lot of HIV and an awful lot of KS. And so I remember sitting on that plane on the second limb, and I made a list on the back of an envelope. That was a napkin, actually, from United, of all the diseases that I was pretty sure were going to be infectious, but for which no etiology had been established. And at the top of that list was KS. Okay. I still remember what number 2 was, which was Kawasaki's disease. Thank God I didn't choose that, because that is still an unsolved problem.
In 1993, you succeeded James Watson as the head of the National Human Genome Research Institute and embarked on what some might say was the most ambitious biomedical project in history, the decoding of the human genome. Can you talk a little bit about the challenges that you faced, the competition with Craig Venter, and ultimately how joyous it must have been to finish the first draft?
Well, it's quite a saga. It's hard to put into a few minutes, but I'll try to hit a high point or two. Well, first of all, how did I end up in this role? Jim Watson was the first director of the Genome Project and was very effective in both generating scientific enthusiasm, which people may not remember these days, was actually pretty limited. At the beginning of the Genome Project, most of the scientific community was opposed to it, thinking that it would be impossible technically. It would end up being too expensive. It would take money away from other things. But Jim, with his remarkable rock star status, was able to give this the kind of credibility, both in the scientific community and in the Congress, that it needed to get it started. But very quickly, in the space of 2 years, suddenly things went wrong, and Jim resigned, and there we were. I had at that point started a genome center, one of the first 6 at the University of Michigan. I was a Hughes investigator. I was happy with my life as a researcher, as a person taking care of patients, teaching medical students. I had the perfect sort of life plan here for the rest of my career, and all of a sudden the phone rings and somebody says, "We want you to apply to be the next director." And I said, "That's crazy. A federal employee? You've got to be kidding. That's the one thing my mother told me never to do, is to work for the government." So I actually sort of ran away from this for a while. But ultimately, the opportunity to stand at the helm of what history, I think, will regard as just about the most significant scientific effort that we've undertaken in the last many centuries, well, how could you turn that down? So with great anxieties about what it would mean, great concerns that the project might fail, because when I started in April of 1993, we were just barely beginning to get going. Promises had been made that this was going to get done in 15 years. that we were going to somehow scale up the ability to read out DNA bases to the point where you could do 3 billion of them in a measurable period of time. And at that point, you know, if you did 1,000 in a day, you were doing pretty well. So it was hugely challenging to imagine how this would go, but it seemed just too interesting to pass up. And because the project was so interesting, and because Jim had started the process of recruiting some of the best and brightest to come and join, and I had the privilege of continuing that, and people got excited about it and said, well, yeah, I don't know what else I could do, but this sounds like what I want to do now. We developed that team, a remarkable group of dedicated individuals, and the energy that went into that, and the creativity as far as technology development, and the ability to work with model organisms, which was a very wise decision of the planners, to be able to understand how you could read large amounts of DNA and begin to understand what that meant. All of that was a solid trajectory. And by 1998, I think we were all beginning to believe that this might actually succeed, although getting it done in that 15-year timetable still seemed like it was going to be a heck of a stretch. There was, at that point, then arriving on the scene, a challenge from a private entity. And that was an interesting juncture, in particular because it brought this project, which had mostly been under the public's radar, out into a much more public space. Not all of that was good, in the sense that there was way too much focus on this being a race for the human genome, and too much focus on differences in technologies. We were all using the same machines. And maybe way too much focus on personalities, right, in terms of who had a yacht, that was him, who had a motorcycle, that was me. I mean, who cares, really? Let's just get this science done. But it did sort of, I think, give us a chance to have this groundbreaking historic project reach the consciousness of more people, and that was a good thing. The real difference, which I think a lot of people missed, was not so much the scientific strategy. It was really the approach of how was the data going to be made accessible. One of the proudest moments, I think, for the Genome Project was that decision in 1996 that all of the data would be made available every 24 hours, immediately, so that anybody who had a good idea could use it, not waiting for publication, not filing any intellectual property claims. And that was a decision which has now reverberated through much of biomedical research conducted by NIH, this notion that open data access is not just a good thing, it's almost a responsibility if you're doing something that other people could use. Obviously, the private sector model could not adopt that, or there would be no possible profit. And I think it's a very good thing when the dust all settled, the ultimate version of the human genome that everybody started using and now uses frequently, many times a minute, is publicly accessible without any restrictions. That was the right answer. And there are no more business plans, I think, of companies that aim to try to generate that kind of very fundamental pre-competitive data as some sort of a database that you would have to pay for. This just ought to be out there. And it is, which is great. So to be able to stand at the helm of that and to work with these 2,500 scientists in 20 laboratories in 6 countries, only about half of whom I had any real authority over because the rest were supported by other agencies. But it was still a wonderful experience.